Hello, everyone, and welcome to today's SANS webcast, Securing Common Web Framework Stacks, sponsored by RunSafe Security. My name is Jessica Gallus of SANS, and today's featured speaker is Shane Fry, Director of Security Engineering, and Doug Britton from RunSafe Security, who will be moderating today's webcast. If during the webcast you have any questions for our presenter, please enter them into the Q&A window located on the control panel at any time. Please note that this webcast is being recorded, and a copy of the slides and recording of this webcast will be made available for viewing and can be found on the SANS webcast archives. And with that, I'd like to turn the webcast over to Shane.
Thank you, Jessica. Thank you, everybody, for joining us today. I'm Shane Fry, as she mentioned. I'm the VP of Security Engineering at RunSafe Security. A little bit about me: I've done a lot in the cybersecurity space, offensive, defensive. A lot of work trying to figure out how to break systems, software, everything from hardware all the way up through web applications. And I'm now at RunSafe Security, leading our tech team as we build out better defenses against memory corruption bugs. So, for the agenda today, we're going to give a brief intro of myself, which I've already done, and talk about RunSafe Security. But then we want to talk about some of our Alchemist technology, its use cases, and then a SANS assessment that we had done by SANS that was super productive for us and is going to, the results of which are highly relevant to customers of ours and potential customers like you that are deploying web application stacks and are focused on your web application security, but are missing kind of a key component of that security posture, which is protection against memory corruption vulnerabilities. So RunSafe Security's mission is to disrupt hacker economics by immunizing software from cyber attacks. So what we are trying to do here is kind of solve the problem of attackers having to just find one hole in a system while defenders have to be perfect. I think everybody on this webinar would agree that that's a problem. It's painful as security practitioners, and we really it's not sustainable to live in that world forever. So RunSafe is trying to solve that through our Alchemist product offering. So what's this cybersecurity gap that I mentioned, though? So in a lot of cases, the most frequent CVEs are memory related, right? And 59% of those kind of spot checked have publicly available exploit scripts. So it's not like it's a huge ask of someone, an attacker, to be able to find vulnerabilities in your software that already exist and have exploit scripts available to them. These memory corruption bugs are also the highest severity. They average 7.2 to 9.8 on the CVSS. I think that's V3 scoring, whereas non-memory corruption severity is usually in 4.9 to 6.7 range. And a lot of times they go undetected by scanning tools. So an unpublished, well, I guess soon to be published NC State study on scanning tools found that only 2.5% of vulnerabilities against the Linux kernel were detected by scanning tools over the last 10 years, I think it was. And so, that's problematic, right? And so as we look at this memory gap or the security gap for memory protection bugs as it relates to web applications, there's a lot of tools out there that are doing great work in web app firewalls and static and dynamic testing tools. But you're still leaving your base web server vulnerable. So this is where Alchemist comes in. RunSafe's Alchemist product offers continuous security across your build and deploy tool chains at really any stage in the life cycle. So whether that's in the build process with our source tool, all the way through to at deploy time, we've got an Alchemist binary tool and Alchemist Repo where we can deploy hardened versions of your existing code or of open source solutions or products that you're using in your solutions. So at a super high level, RunSafe Alchemist works by taking in unprotected software, either source or binaries, transforms them, and then produces protected software. And so that transform looks a little bit different based on what technique is being applied. So we're going to get really technical really quickly, and we're going to stay here throughout the rest of the presentation. And so on the left, we have a Hello World program, pretty standard. It's got a header, a text section, and a bunch of functions in it. And then we've got our LFR capability, load time function randomization transform, that we are, that's part of our Alchemist source module. And that takes those functions and randomizes them in memory. What we're doing there is removing an attacker's ability to use ROP and JOP type attacks against memory corruption vulnerabilities. We'll also talk about protection against return to libc type attacks in a little bit, since that's what was used in the assessment. And then we've got two binary-based approaches that shuffle basic blocks inside of functions or modify the stack frame in a for a given function. But since we're talking about Alchemist Repo today and the assessment that SANS did, they took a look at software that was protected with our load time function randomization. So if we take this same Hello World program and we protect it with Alchemist Source's LFR module, we get a few different changes. We add a new function into the binary. We add some metadata about the binary that allows us to do the randomization. We then randomize the binary and resume execution. So every time the program is loaded, every time a shared library is loaded, we randomize it, and then that allows you to get that randomization that's unique per process. And then we go back to the original entry point over here at the end of the process, and we're out of the way. So execution at that point is just as fast as it was before, just as performant. There's no agent overhead. There's no outside process looking in, introspecting. You're not getting a 30% performance overhead for CFI, et cetera. So what are some use cases? Alchemist is deployed in critical infrastructure for embedded systems, enterprises with IT infrastructure, open source solutions, et cetera. It's applicable to manufacturing and military systems that are highly customized and specific, but then also for software companies that are just producing software for businesses or consumers to use. So we're talking about web stacks today and how do we secure those. And one of the ways we do that is through an offering that we call Alchemist Repo or Alchemist Repository. And what we've done is we've basically taken a set of existing open source solutions that are in pretty much all IT infrastructure today, and we've done the work for you of applying our Alchemist LFR transform to that software. So you can just take your existing solutions and move them into Docker, move them into a protected state with very little change. So currently we have 7 different repo offerings: Postgres, Redis, Python, Node, Nginx, Memcached, and Apache, with a few different versions of each and a few different base OSs. So we basically support what the original open source provider supports in that regard, as far as Alpine versus Debian versus Ubuntu images. And if you don't see what you need, you can send us an email at support@runsafesecurity.com, and we can look into adding that for you. Now, a lot of tools out there say they're really easy to integrate, they're really easy to use, but that's one thing that we've seen in our lives as attackers on the RunSafe team and also as defenders, is if there's any place for steps to be skipped or for tools to be misconfigured or installed the wrong way, security is going to fail or users just won't do the work. And so we really wanted to make this integration really simple. So on the top of this slide here on the left, you can see a Docker file that is going to copy some files in for an Apache web server to serve. And so you see a from HTTPD 2.4, and we're going to copy in our public HTML folder into the location in the Docker container that Apache needs it. And then from there, we will build that Docker image and run it. So that's pretty straightforward, not a lot to it. But how do we get repo? Well, all we're going to do is add to the start of this from line here a special string, RunSafe security, Docker Alchemist ESP, .jfrog, and that basically points to our Artifactory instance where we host our repo images. And then we add in a flag to our Docker run command to specify an Alchemist license key. Now, I'll send you the link on the last slide where you can get your Alchemist license key, but we offer a 30-day free trial, no credit card required. Go to the website, sign up. You can get your Alchemist license key. You can go through some online demos on our portal, and you can actually do the integrations and see the software work for yourself. So your license key will go here, and those are the only two changes, these two changes in green. So now let's get to the meat of the presentation here. So the RunSafe security wanted to have a third-party assessment done by SANS or by a trusted name in the security space to make sure that the solution that we're selling actually does what it says it does. As an engineering person, as someone that's done a lot of offensive research, companies that say their solution works when it doesn't really bothers me. I don't like snake oil salesmen. So it was important to us that we have this assessment done. And so one of the things we wanted to do was have an independent SANS researcher find an existing CVE or multiple CVEs that was recent, was in commonly deployed software, and there was source available to it so that we could apply our source protections to it. So SANS's methodology was kind of a two-step process, and I'm really simplifying this here. They did a lot more as far as research and testing and whatnot, but basically they wanted to compile the application that they picked without protections, show that the exploit worked against that application, and then recompile with Alchemist to see if that protection worked as we said it did. Now, the first step is really important because exploits are often very fragile. And so we want to make sure that anything that we're testing breaks because of the protection in place, not breaks because the exploit is fragile. So in this particular case, SANS did not use existing Alchemist repo images because we needed a very specific version of software, and we did not have that version of software in our repo. It's a pretty old version of Apache that this vulnerability existed in. So we could have done that for them, but they wanted to do this outside of repo for that. So what they did is they went in and found the software and then compiled the open source software themselves with Alchemist source. So, and I seem to have missed a slide here. Let me come back to that. So with our web servers, I mentioned this earlier, a lot of people are really focused on doing static and dynamic testing, deploying WAFs or RASP tools on the interpreted side of their web app code. And that's great. I definitely recommend you continue to do that. But we have to acknowledge that there are limitations to that from a security perspective. So what about the compiled code that's hosting it? People that are running Apache or Node or Nginx, if you're doing Node and Nginx, you've got compiled code in Apache. There's compiled code that's actually hosting your website. And the HTTP protocol has a lot of ability for people to misinterpret the spec and misimplement that spec with security bugs when they build that in. As you add more modules to it, as you talked about Node and Nginx and Apache having modules, those modules can also introduce security vulnerabilities. So what about the OS that's running underneath those web applications as well, right? So we want to be able to protect ourselves at the interpreted code layer for your web apps from cross-site request forgeries and SQL injection and command injection, stuff like that. But we also want to make sure that the compiled code underneath it is being protected. So the vulnerabilities that were picked were basically two different vulnerabilities: a PHP use after free, which ended up being a 0-day, PHP was alerted to it. They said it's not a bug. And so the researcher just released it as 0-day, so there's no CVE number for that. And then the Apache CVE, which is 2019 0211, also known as Carpe Diem. So we've got two exploits. We've got a use after free in PHP, and then Apache has some out of bounds writes. Well, really it's a privilege escalation through the PHP use after free. And then putting it all together, we end up with remote command injection via return to libc as our final stage in the attack. So before we do that, let's go and show that the Carpe Diem exploit is functional in the environment. And oops, I've got a video for that. So what we've got here on the left and right is a Debian stretch image running the vulnerable versions of Apache and PHP. So on the right, we've got the command that is used to trigger that PHP use after free. So we're going to curl to a website that has the malicious PHP script on it and passes a command to it to say, what are we going to do when we're done here? And this command is what gets sent to the system function to execute. So in this case, we're going to copy etc shadow, which stores the passwords on a Linux system, to root/seizedit. And so we're going to run that here on the right. And you'll notice that the script says exploit successful at the bottom. And that's the PHP script responding that it was able, the use after free was able to happen. And so we're going to run this a few more times just to make sure that we get the best chances at the exploit working. And then on the left side, we'll end up running a script that we wrote, or that SANS wrote rather, to just check that the exploit actually worked. So it's going to restart Apache, and we'll see that etc shadow got written to root seizedit. And we do actually delete this seizedit file before if it did happen to exist. But we'll see when we show the exploit failing later where that doesn't work. So in this case, we've got the environment with PHP and Apache, the right versions for the use after free and the privilege escalation, as well as the return to libc attack working. So now let's go back to the slides and let's dig into the vulnerability here. So once SANS got the example working, they hardened our code, or hardened the PHP and Apache with Alchemist LFR, and the exploit still worked. Well, that's not good, right? We're here to tell you about how our code works and how its protections are. But remember, I said that we don't want to be snake oil salesmen. So one of the great benefits we got out of this research with Chris Crowley and Waskar Tejada was that we had a hole in our protection. And this particular vulnerability, Carpe Diem, showed that to us. So we paused the effort briefly. SANS reported the bug to us, the vulnerability still working. And RunSafe went to work to try and improve our product to make it better. So we're going to dig in. Basically, what we were doing here was, I mentioned it's a return to libc type attack, and we weren't protecting libc. So the exploit was able to run just as usual. So we'll get into the specifics of that in a few slides. So the first thing we want to talk about is the PHP code. So we curled a PHP page, which is actually what's running the exploit. So how might that get delivered in the wild? We want to make sure this is kind of realistic, right? The attacker needs to get that PHP attack code on the target server. And you might see that in an environment where you've got an MSP or a web hosting environment where you're allowed to host web applications. And they may have some security that's, cordoning off different things. But if that's the case and I can upload PHP, then I could break out of that security sandbox. But you might also get your malicious attack code onto the system through a directory traversal vulnerability or a web app plugin vulnerability. So everybody out there that's running WordPress or all these other kind of blogging and web management, website management platforms have plugins. Those plugins can have vulnerabilities. It's a pretty big problem in the web space, as I'm sure you're all aware. So there's many different ways to get malicious PHP code onto a target server. And so we're going to assume that an attacker's been able to do that for this. So now let's dig into the PHP use after free flaw. And the source of that is from Charles Foale, and he has an excellent write-up on his website and proof of concept exploit code, which is what SANS used as the basis of their exploit here. So I wanted to give credit to Charles for that. So use after free basically occurs when an array is defined in the program source and it gets unset in an object, but then the object itself saves that array, and then you can access that value, that memory space from that object instead of from outside of that space in the global space. So here we've got a class X, which extends a date interval, and it's got just a JSON serialized function. Doesn't really do anything with JSON, but just to name it whatever you want. And we have these globals. We're going to unset the first element in an array here, and then we're going to set a pointer to that value that we just unset, since the original value for Y there happens to point to the first value in the array. And then we're going to return the class to it. So now we're able to access that memory through this date interval object, which happens to allow us to set things like day, month, year, hours, minutes, seconds, which is later going to be used to allow us to arbitrarily read and write memory. So this use after free basically gets leveraged to identify shared memory objects in Apache. Apache spawns off a process for PHP to handle these requests. And so PHP can read into that memory space and the shared memory between those two processes and identify certain objects that have a very similar structure and a very similar set of data in them. So it's easy to find those memory addresses. Then we're going to overwrite those addresses. And then when Apache does a graceful restart, Apache is going to use that information to go do some work, and we're going to get execution through that. So basically the flow of the exploit, there's a lot of complexity to it, but at a high level, there's maybe 5 things that are happening. We create a custom object that extends a date interval, and then we're going to create a Zen string object that's going to end up in the same place in the heap where the date interval object was, where we unset a certain value. Right. Then we're going to use that Zen string object to read and write heap memory by modifying the length of the string. So this is essentially kind of a type confusion attack, but it's not directly that because we're not casting the date interval object to a Zen string. We're just going to modify the date interval object, which will happen to write to data where that Zen string object actually is. So then we're going to find these APR proc mutex T structures in memory. We'll talk a little bit more about what those do in a few slides. And we're going to overwrite a pointer in them to a function or method called child init. And so that child init method is used by Apache later to run code and restart any jobs that were happening. So when Apache does a graceful restart, it has to not drop all the work that it was doing. Otherwise, you'd have a lot of APIs that fail, a lot of web servers responding with error codes. So there's a way that Apache can stop a process that's doing work and restart it later. And that's through this child init function on the APR proc mutex T object. So in this vulnerability, the PHP code goes through and reads the shared memory to find structures that represent the child processes in the Apache space. So Apache keeps a list of all of the processes that are doing work and information about the work that's being done. And so the PHP script is going to go through and find all these processes in memory and then overwrite them with fake structures that look reasonable enough to the real structure. But as I mentioned on this previous slide, we're going to overwrite that child init to point to an invalid or a different pointer, a different function than it was intended to. So here's where we're creating kind of a fake object here. And the child init method ends up pointing to the Zend object Destructor. So the Zend object is kind of the base object in PHP. And we're going to basically point to that object Destructor. And why that's useful is Zend objects have properties about them. And so those properties are where the exploit is going to save the command that we want to run as an attacker, and it has a pointer to the actual destructor to call itself. And so when we call this destructor, we're going to call the properties destructor, and that's going to end up being how we get code execution on the system. So here we can see this property structure on the right, and it has various things like a reference counter to it, the number of elements, table size, a few other things. And we're just going to put some values in there. But the important part is this UN table mask, which is going to point to the structure that we just defined in the previous slide. And then AR data here is going to contain the payload to execute. So if you remember from the video, we're going to be executing copy from Etsy shadow to root seized it. And then at the very end, we've got a destructor here. And we're going to point that to system. So what's interesting here is you see this as addresses system. This PHP script is actually going to go through and find the address of the system function based off of the libc binary on disk, but we'll talk about that in a few slides. So now that we've created these property objects, we need to kind of spray them into memory so that when we go to do the attack and get the Apache process to do what we want, we need those objects sprayed in memory. So we're going to do a heap spray for that. And then we're going to use our read write primitive from the Zend string to identify the worker process IDs and update each of those objects with the pointer to what we've shared or what we sprayed into the shared memory there. And that just gives us a better chance of the exploit working. You don't have to do this for all processes, but it helps it be a little bit more reliable and robust. And that's actually one of the cool things about this proof of concept from Charles Hole is that the exploit is actually really robust, which you don't see a lot of the times these days. So we leave one of the worker buckets, one of the child processes gets unmodified because we need it to accept the payload that we're going to send it as an attacker to be executed by that system function. So the PHP code accepts the command to run as a get parameter. So you can see that here we get the command from the request object. And if it's not set, we're just going to run chmod plus s on Python 3.5. But we pass that in to copy that Etsy shadow file off the system. So that's the PHP use after free side. So that's going to go through, modify all the memory that's needed, but how do we get code execution out of that? Well, the answer is Apache's Graceful restart. So in Apache, the parent process runs as root, and that's really important. So the parent process runs as root and then spins off a bunch of child processes to handle all the requests that come in. So once the child processes get working, at some point Apache can do a Graceful restart. It happens to do this once a day. For log rotation, you can configure it to be different times, or it may just be done for maintenance purposes by an IT system administrator. But when you do a Graceful restart, the parent process never quits. So what happens is the child processes that aren't running as root get terminated, and then new child processes are created to handle those web requests that were already in process. So what this does is it gives you the benefit of being able to continually operate and serve web content without disrupting operations to your users, to your other systems. So Apache's Graceful Restart is often used for log rotation or to reread configuration files. So if you're changing your HTTPD conf, for example. Now, if we had our PHP use after free and the system was configured to not do a graceful restart, but to just daily do a hard restart, the Carpe Diem exploit would not be applicable and wouldn't work. So keep that in mind as you go through. This is only allowed because Apache does a graceful restart once a day, triggering the vulnerability here. So what happens with the Carpe Diem side of the exploit, the Apache side, is Apache's Prefork C, which is what spins up those child processes. It doesn't adequately verify the shared memory that all the child processes were operating in to make sure that the values and the data that's in there is valid. So when that PHP process goes through and modifies the structures in memory and then gets restarted, Apache doesn't detect that malicious modification. So let's dig a little bit into the Prefork C Apache code that contains the flaw. So as I mentioned, Apache starts as root and then spawns a bunch of non-privileged child processes. Now, what's relevant here to note is that when you fork exec a process, you don't get to specify, here's the user ID, right? The fork happens and then you've got to drop process. And so that doesn't happen immediately. So what we have is, and that's one more slide later, sorry. So for seamless execution, because the child might have been doing something that was important, the parent process says, is there any work available that you need to finish up? If so, go finish that work and then we'll hand you a new request. And so the parent tracks those processes via this scoreboard data structure that we're not going to really dive into. And then the child processes write status and tracking information to that scoreboard, which is in shared memory, and which is how the PHP use after free allows us to trigger this exploit. So because these child processes can modify the structure of that scoreboard before the Apache graceful restart occurs, you can modify those structures and then affect execution when the new child processes start up. So if we look into the actual Prefork C code, the vulnerability isn't here, but it's close to here. There's a highlighted part here that says need to be done before we switch UIDs so that we have permissions. So there's some work that Prefork is doing to set up the environment that needs to be done as root. But then they don't verify that the data is trusted and correct before doing that work. And that's what leads to the vulnerability here. So this safe except function has a couple of conditions that have to be passed, but the exploit goes ahead and handles that for us. And then when this runs, this APR proc mutex child init gets run, the process ends up running as root instead of switching to a less privileged user ID. So at this point, we've got the PHP use after free that has modified our child init method and pointed to an object destructor. And then that object's destructor points to the memory address of the system function. AR data, as I mentioned from the property earlier, points to the address where the attack code is stored. And then system gets called with the command that we want to run. So how do we disrupt that? Well, first of all, the PHP code actually does something really cool. And because PHP is a very powerful scripting language, it can go and actually open the file proc self maps to get the base address of libc. So Carpe Diem, as it's written right now, does a return to libc type attack. And instead of having to find an information leak and defeat ASLR, it can literally just read the process map and parse the base address of libc. Well, that's interesting. Cool. So now we defeated ASLR. That makes this exploit way more reliable. And then it reads the libc binary and parses the ELF structure, finds the symbol for the system function in memory, and computes that final address to say, well, this is where we're at, where the system is at. It's at the base address plus that offset. And so when it's populating its structures in memory, it knows exactly where to go. So to disrupt that, and this is the limitation that we had that I mentioned earlier, we've got to apply Alchemist LFR to libc, and that is oversimplifying some internal changes we had to make to our tooling and our product to allow that to work. But once we applied LFR to libc, then when libc gets loaded, all of the functions in libc get randomized, and then system's offset in memory is no longer the same. So if we go back to this slide here and we see the system offset, then that's not going to be the same every time. And then as a result, the PHP use after free can no longer reliably point to the address of system. So now let's go through a video of the Carpe Diem exploit failing. So similar to what we had before, on the right, we've got the script to go through and do the PHP use after free. And you'll see that it still says exploit successful. We're not impacting the ability of PHP to read and write memory. So the use after free is still going to work, but what we end up disrupting is the attacker's ability to use that use after free to gain code execution on the system, to get remote command injection, in this case, on the system. And I guess it's a little bit of both. It is code execution that turns into command execution. So we run it a bunch of times on the right to get us a reliable use after free. And we see that on the left, we've gracefully restarted Apache, and we still have that same hash for Etsy Shadow, but the root seized it file did not get created. And again, that's because the attack tried to call system, and system was not where the attacker expected it to be. So in conclusion, the SANS-led research led to improvements in Alchemist source protections against memory corruption attacks. And I just want to call that out because we very much appreciate the work that SANS did, that Chris and Laskar did. And then also, though, memory corruption attacks can still impact web applications. We've gone through and shown one example here of PHP and Apache being attacked. That's not in a way that a web app firewall is going to catch. That's not in a way that static analysis tools are going to catch, because they're focused on a different part of the system. So we really still need to be able to, when we're thinking about the security of the entire solution, we want to make sure that we're considering the web application code, still protect that, still do all of the best practices there, but also focus on getting those memory corruption attacks protected as well. So we've seen where we can deploy Alchemist Repo to protect against those memory corruption attacks. It's really simple. It's 2 changes to your Docker files, but it's there. It's something that we can do really easily. And you'd be able to deploy a hardened version of Apache today that has these protections built in. And adding it is really seamless. It doesn't involve changing your DevOps flows, your DevSecOps workflows. You don't have to hire 5 engineers to babysit a tool all the time. There's no security false positives or false negatives. You just kind of get the protection. And so you can start your trial and be up and running in literally minutes. It really does not take long to get your software moved over and being protected just quickly. So I mentioned earlier, there's you can get a 30-day free trial if you go to alchemist.runsafesecurity.com, or you can scan the QR code here. It'll take you there. You can create an account. Like I said, there's no credit card required, but you can go in and sign up for an account and get running today, both with Alchemist Repo and our Alchemist Source offering as well. Does anybody have any other questions? It looks like we've had 3 questions, and Doug has answered those in the Q&A panel.
Yeah, no other questions so far, Shane. Anyone wants to raise a hand? We could also let you ask the question live. Well, right. Yeah, we can, Jessica, we can pass it back to you, and Shane and I can hang out for another couple of minutes if there are any other questions.
All right.
Yeah, Jessica. Go ahead.
Thank you, Doug. I actually do see a question that just came in. It mentions, how do I see what software versions are available in Alchemist Repo?
Yeah, it's a great question. So if you go to the alchemist.runsafesecurity.com, at the very top, there's going to be a deploy button, and you can go in and click deploy repo, and that will show you all the software versions and tags that we have for Docker today. And there's also a beta of a tool out there that will allow you to copy paste your existing Docker files, Docker compose files, or Docker run commands, and hit a button and get that one click changed over to repo versions of those images.
Okay, great, thank you. Another question kind of goes from the one that you just answered, which is, does Alchemist Repo only support Docker releases?
At the moment, yes, although we are working on being able to provide hardened versions of existing RPM and Debian packages. So we'd be able to cover Debian, Ubuntu, CentOS, RHEL versions of software that's already out there today. So we should have that, in the near future, but for now it's just Docker.
Okay, great, thank you. Last question that I see is, I use software that isn't in the repository, such as MariaDB. Can you add that?
Yes, so if there's software that you use in your day-to-day operations, in your production stacks, in your test stacks, that you don't see in the repo list on the Alchemist website, you can email support@RunSafe request. Usually it's pretty quick for us to turn those around, but we're happy to get feedback from users on what software would be important to them to have to make repo more valuable to them. So again, you can email support@runsafesecurity.com.
Okay,
great.
Oh yeah.
Also make one other point. Our tool to create the hardened versions is it's our Alchemist source tool, which is the exact same thing that we're using to harden the repo packages, but you can use it for any of your own internally developed software or any other open source you pull in. If there's libraries, embedded, big IT, little IT systems you'd like to compile, and that could be on ARM or x86, then you would be able to build those, whatever code you'd like to build. And then you can get that same trial underway at the same link on the screen.
All right, thank you, Doug. Do you, Shane, or Doug have any other closing thoughts before we end it?
I appreciate the team yeah, I appreciate the SANS team. It's been a pleasure to work with them. And Shane, thank you, sir.
And thank you to everybody for joining us today. We know time is very valuable. So thank you for joining us and learning about this.
All right. Well, thank you both. So that's all the time that we do have for today. Any unanswered questions can be sent to q@sans.org. Thank you to our speaker, Shane, and for Doug for helping with the questions, and for that great presentation with RunSafe Security sponsoring this webcast, which helps brings this content to the SANS community. To our audience, we greatly appreciate you listening in. For a schedule of all upcoming and archived SANS webcasts, including this one, please visit sans.org/webcasts. Until next time, take care, and we hope to have you back again for the next SANS webcast.